We're now going to take a look at a few examples involving z-scores. So in this example, we're given two sets of test scores from two different classes. And what we want to do is calculate the z-score for the score of 70 from class 1, that's this score here, and the z-score for the score of 65 from class 2. And then we want to determine which score is higher relative to the rest of the class. Now, using our intuition here a bit, we can sort of get an idea of which score is higher relative to the rest of the class. For example, if we look at the 70 here, we see that all of the other scores for class 1 vary from, excluding the 70, vary from 84 up to 87, and then you have this one score of 70. So that's a pretty low score relative to the rest of the class. But if you look at class 2 and you look at the score 65, you see there are some other scores that are lower than 65 in the class, and there's a lot more variability in the scores from class 2 than there are in class 1. So it looks like the score of 70 is actually lower relative to the rest of the class than the score of 65 is in class 2. But let's see what the z-score tells us. Now, to calculate the z-scores for each of these, we want to use this formula, where x bar is the sample mean, s is a sample standard deviation, and x is the particular score, in this case either 70 or 65. Now here we have the z-scores for each of the scores right here calculated. And let's just go through the process of how we obtain those two numbers. So if we enter this data into Excel, that's what you'll have to do to calculate the mean and standard deviation. So here we have the scores entered into Excel right here. And we want to calculate the z-score for 70 and for 65. So we need to calculate the mean and standard deviation for each data set. So the mean, we just use the average function. So there's our mean for class 1. We can copy that right over for class 2. And then the standard deviation. Now be careful, we want to use the sample standard deviation. That's this one. That uses the formula where we divide by n-1. Remember, the population standard deviation, you divide by n in the formula. Normally, usually, you want to use the sample standard deviation. So .s. There we go. And we can just copy that over. So there you go. We have the mean and standard deviation for each class. Now the z-score for the score of 70, we just have to evaluate 70 minus the mean is in cell B12, and then divide by the standard deviation, which is in cell B13. And there we go. There is our z-score. Negative 2.79. And the z-score for the score of 65 in class 2. Okay, so that's 65 minus what's in cell C2, which is the mean for class 2. Divide that by the standard deviation, which is in cell C13. And there you go. So here is the z-score for 70 from class 1, negative 2.79, and the z-score for the score of 65 from class 2 is negative 4.6. And looking back at the class notes, you see we have the z-score for the score of 70 being negative 2.79, which is what we found using Excel, and the z-score for the score of 65 from class 2 is negative 0.46. And also notice that since negative 2.79 is less than negative 0.46, the score of 65 from class 2 is actually better or higher than the score of 70 relative to the scores in each class. Now let's take a look at this example. Now for this example, this uses the same data set for the classes that we just looked at. We want to classify the scores of 70 and 65 as either ordinary or unusual scores. Now to do that, we're going to use the definition that's in your notes right here on the previous slide. So having calculated the z-score for each of those scores, we just have to determine which of these two cases we're in for each score. So we already calculated the z-score for the score of 70 to be negative 2.79, and we see that that is less than negative 2. So this score would be considered unusual or unusually low. On the other hand, the score of 65 has a z-score of negative 0.46, which is between negative 2 and 2. So that score, the score of 65, would be considered to be ordinary. And let's take a look at one more example. Now here we're going to go back to the height of women again. So for this problem, we're going to assume the distribution of women's heights is once again bell-shaped with a mean of 63.6 inches and a standard deviation of 2.5 inches. So the first question we have is, would a 6-foot tall woman be considered to be unusually tall? And would a 5-foot 6-inch woman be considered unusually tall? Well, we have to look at the z-scores for each. The z-score for a woman that is 6 foot tall, now we have to convert the 6 feet into inches. 6 feet is 72 inches. So if we look at 72 minus 63.6 over 2.5, that's going to give us the z-score for the 6 foot tall woman. And that comes out to be 3.36. And that is greater than 2. 3.36 is larger than 2. And so yes, a score of 6 feet or 72 inches would be considered unusual or unusually high. Now for the 5-foot 6-inch woman, we have to convert 5 feet 6 inches to inches. Well, that turns out to be 66 inches. And so if we look at the z-score for 66, we evaluate 66 minus 63.6 divided by 2.5, we come up with 0.96. Now notice that that number is between negative 2 and 2. So that's between those two numbers, and so that score would be considered to be ordinary. It is not unusually high or unusually low. So the score of 5 feet 6 inches is just ordinary. And that concludes our discussion about z-scores.